In this lecture, we look at traveling and standing sound waves and the phenomena of resonance. Here we have an actuator which sends traveling waves down this tube of air. You might notice that we stop the demonstration or the demo before it reaches the end of the tube because there's going to be a reflection at the end of the tube. There's a discontinuity between the enclosed space of the tube and the open air. That discontinuity will cause reflection. The superposition of incident and reflected waves will lead to standing waves, as we've seen in our previous lectures. For an open tube, it must have nodes at the two ends. The density must match the density of open space. So the lowest resonance frequency, or the fundamental, only has nodes at the end. And here's an example of that. So we have that the nodes at the end match, so the light color of the open air is matched in this picture by the light color or light density of the dots on both ends of the tube. The wavelength for the fundamental is this distance between the two nodes is lambda over 2 is equal to the total length of the tube, or in other words, the wavelength is equal to 2 times L. The next highest resonant frequency also has a node in the middle as well as at the ends, so that we have this picture here where we have, again, low density at the two ends and two regions where it goes from high to low density on the left and right hand sides of the tube. In this case, for this next highest resonance frequency, lambda is equal to the total length of the tube, so lambda is equal to L. Let's look at an example of a resonance of a water pipe. A long pipe connects two large tanks of water. A speaker in one of the tanks slowly increases its frequency. What frequency matches the fundamental of the water pipe? The length of the pipe is 5 meters, and the speed of sound in water is 1,482 meters per second. You'll notice that it is an open tube resonance problem. There's water in the pipe and at both ends. For an open pipe, the fundamental resonance occurs at the wavelength. Lambda is equal to 2L, as we saw in the previous slide. The speed of sound is equal to the wavelength times the frequency. So if we divide by lambda, we have V sound divided by lambda is equal to the frequency, so that the frequency is equal to 1,482 meters per second divided by the 10 meters, which is equal to 148 hertz. For comparison, if this were an open pipe in air, frequency of air is equal to the speed of sound in air, 343 meters per second, divided by the wavelength, which is still 10 meters, which is 3 hertz.